G'day, welcome to our discussion today of inverse functions. Our general topic is when can we undo the work of a function? We've talked about a lot of different kinds of functions so far this semester. Today we're going to talk about when we can undo what those functions do to numbers. So let's start with an example. Let's start with maybe a somewhat silly function. We're going to start with this grinder function that you see over here. And we're going to feed into this grinder function our variable. And with apologies to any vegetarians, our variable is a cow, I guess. We've got this function, the domain of this function, the grinder function, is, well, cows. And the output of this function, leading to the range of this function, well, let's just say it works well on a barbecue. So can we undo the work of this function? We take the input from the domain, we plug it through our function, we get an output in the range. Clearly this can't be undone. We can't reverse this process and turn our sausages back into a cow. If we think more mathematically, a function is simply like a black box where we feed something in and that something comes from the domain, the x. The box does something to the values of that function, and what comes out is f of x. In fact, I've labeled this wrong. This is not really f of x on the inside. This is just our black box function. This is our function f. And this function takes numbers and produces other numbers. In the case of this grinder function, it takes cows and turns them into sausages. What we're asking is, given the output of one of these functions, can we go backwards and get the input back? Which in this silly example is asking, can we take these sausages and reproduce the cow? And obviously you can't, and the same is true mathematically. Not every function has an inverse. So today our topic is going to be, when is there actually an inverse function? Well, here's a more mathematical example. If I've got the function 3x plus 2, can we undo the work that that function does? I think you can convince yourself that we can just by looking at the graph. Fundamentally, you can see that if I give you any value that comes out of the function, well, the things that come out of the function, the y values, which we plot on the y-axis, these y values, the values that come out of the function, if you give me one of those, for example, you were to give me the number 3, let's say, then I could trace this back to the input that produced that number. For example, if I wanted this function to equal 3, then I would just say, well, 3 is coming out of the function, what was x? And so we can reverse this process, and we would get 3x equals 1, so x is 1/3. So if I want to know what produces 3 out of this function, the answer is something that we can work out. It's 1/3. The value 1/3 in the domain corresponds to the value 3 coming out of the function, in the same way as these cows might correspond to some lovely beef sausages. As our second example, let's consider this polynomial. We can see that this is a parabola. The vertex here is at the point 1 minus 2. It's been moved 1 unit to the right, 2 units down. If we look at f of 0, we can calculate the y-intercept, and so that's at minus 1 squared. Take another 2, so that's minus 1 overall, and so we can sketch a graph. Here's the basic shape. The vertex is at 1 minus 2, and the y-intercept we found was minus 1, so this looks roughly right. So here's our graph, y equals f of x. And what we're asking is, can I invert the work of this function? So for example, if this function was equal to 4, and let's say this is the line y equals 4, if this function is equal to 4, f of x equals 4. I know that 4 comes out of the function. Just like the sausages before came out of our grinder function. If 4 comes out of the function, do I know what I put into it? If I get 4 coming out of the function, then I could have put in this value of x, whatever it is, this is y equals 4. Or I could have substituted this value of x. So there are two possibilities. But I know that a function can only possibly give you one result. A function only gives us one value. And that tells us that there's no inverse function here. This quadratic, this polynomial, has no inverse function. Because there's more than one value that could have produced the 4. And if there's an inverse function, then I absolutely uniquely must know what value I put into the function to get 4 out. So let's contrast what we saw in this example with the previous example. Here's the graph from the first example we did. We know that there is an inverse function here, because if I tell you what value came out of the function, in this case we said, the function was equal to 3. We've plugged in some value that makes the function 3. And we can look and say, well, we absolutely know that must have been a third, because that's the only place the function is equal to 3. Look, there's a horizontal line where y is equal to 3 everywhere along that line. And so there's only one place where the function, that green line, has the value of 3. And that's at this one place, and so there is an inverse function. I can say that the inverse to this function, which I'm going to use this notation for, is 3. I'm saying, what value must I have plugged in to get 3? The answer to that is 1/3. And that follows from the fact that we learned from the graph, we learned from the calculation, that if I plug 1/3 into the function, we get 3 out. So if I plug 1/3 into the function, 3 comes out. That's what we found. And so if f of 1/3 equals 3, I'm going to say that that means that the opposite idea, the inverse value, is, well, the inverse function is written this way. So the inverse of 3 is 1/3, because we can think about this as taking us from the domain to the range and back again. So here's a nice little visualization. I'm thinking purely of our first example right now. If we look at this function, if I pick the point 1/3 in the domain and plug it into the function, then the function produces 3 for me. Plug 1/3 in, look, the function produces 3. This inverse function, that's the thing we're interested in today. The idea with the inverse function is, if I give it 3, it tells me where we started. So it takes the 3 and maps it back into the domain. So it takes a value from the range, this 3, and tells me what value of the domain we started from, if we're thinking about using this function. So it undoes the work of the function f. And we've seen that not every function can be undone. We've seen precisely that this quadratic cannot be undone, because if I try to undo the work of that quadratic, well, I find in fact there are 2 values that could have produced, in our example, could have produced 4. There's 2 values that could have produced 4, means that I can't absolutely tell you what the inverse of 4 is for this function. So if I say, and this you can think of as a question, for what value of 4, for what value produces 4 from the function? And I've got no unique answer to that. In other words, if I got 4 out of the function, what did I plug into the function? That's what I want to write here. And I've got no unique answer for that, and so there is no inverse function, because functions give a unique answer. So graphically, we can look at this and get a deep insight into when we're not going to have an inverse function. Look at this case. We said y was 4. There were 2 places where the function had that value. Therefore, I don't know what the unique single one is, because there was no single one. Whereas over here, we said, what values does the function equal 3? We said there was a single value, and that was the inverse. That allowed us to write this down. So let's define precisely when a function has an inverse. We define a function to be 1-to-1 if every element in the range, every number in the range, every number that comes out of that function is associated with exactly one number in the domain. And we can see that this fits the idea we saw in the previous example. Here are our 2 examples again. If I give you a number in the range, then to be 1-to-1, that value in the range, that y value, has to be associated with exactly one number in the domain. And we can see here there are 2 numbers in the domain, 2 x values, that this single y value is associated with. In our example, I was using y equals 4, so y equals 4 corresponded to 2 different x values, and so this parabola is not 1-to-1. Whereas the line, on the other hand, if I give you any value in the range, so we're always looking at the range first, so if I give you any y value, then you can uniquely decide what x value that corresponds to. So this one is 1-to-1. And that essentially captures the idea of when a function has an inverse. We can summarize this idea that we've been discussing by saying that a function has an inverse if, and only if, f is a 1-to-1 function. So in particular, if f is a 1-to-1 function, then we know it has an inverse. So 1-to-1 functions will serve as a test for whether a function has an inverse. So let's express this idea of 1-to-1 functions a little more mathematically, and you can see it up here. This is our formal definition of a 1-to-1 function. We say f is 1-to-1 if f of x1 equals f of x2 implies that x1 equals x2. What does that mean? Well, let's go back and look at this picture. Let's look at the quadratic. There are 2 values here for x that have the same y value. x1 and x2. If I plug in and ask what's f of x2, so if I calculate f of x2 here, I find some number. In our example it was 4. And if I calculate f of x1, I find exactly the same value. F of x1 and f of x2 are equal. But the problem that we had was that x1 and x2 themselves were not the same number. And so this is not one-to-one. It is one-to-one if x1 and x2 work out to be the same number. So if you look over here, I could give this same point here, I could give this point two different names, x1 and x2. Then obviously f of x1 and f of x2 are the same. I've just named the point, I've given the point two different names. And so the y value is the same. The y value is just f of x1 or f of x2, depending on which one that you want to use. And the idea here is there's no other value of x. Here, I pick a value of x over here. Well, that gives you a very different y value. So it doesn't satisfy that these 2 points are the same. These two values are the same. And that's because it's one-to-one. Because it's one-to-one, every single time I tell you that f of x1 and f of x2 have the same value, what I'm telling you is, actually I've just given the point two names. Whereas if it's not a one-to-one function, that's not going to be true. There's going to be 2 points where the y value can be different. Sorry, there's going to be 2 points where the y value is the same, but the x value is different. So how do we use that? Let's go down and look at an example. Let's take a function, maybe just a straightforward linear function. Let's say that our function is 3x plus 2, just like before. We know this is one-to-one. So our idea here to use this method is to suppose that f1 and x2 are actually the same. What that means, in our case, here's the function, that means 3 lots of x1 plus 2 is equal to 3 lots of x2 plus 2. Just using the idea. When I'm trying to make an argument like this, if I'm saying if this happens, well, let's just suppose it happens. If x1 and x2 are the same, the values out of the function are the same for x1 and x2, that means let's just suppose that's the case. F of x1 equals f of x2. Well, just following through on the algebra now, we can subtract 2 from both sides, and that leaves us with 3x1 is equal to 3x2, and then we can cancel the 3's, and that tells us that x1 is equal to x2. And that satisfies our definition of one-to-one. We started by supposing f of x1 and f of x2 are the same. There it is. And what we ended up finding algebraically, without a doubt, was that x1 and x2 were the same. And so that tells us that f is one-to-one in this case. Let's look at another example where we determine if this quadratic is one-to-one. And after the preceding discussions, you might have an answer to that already. But let's use the idea. What we're going to do is suppose, or just set, f of x1 and f of x2 equal. So let's suppose there are 2 points, and the y values are equal at those 2 points. That's what we're doing. These are 2 points, x1 and x2, and we're supposing the values that come out of the function, therefore the y values are equal. So just using our function, this is x1 squared plus 3, this is x2 squared plus 3, and I could subtract 3 from both sides, and that leaves x1 squared equals x2 squared. Great. So that tells us that x1 is equal to, well, we took a square root, so it must be plus or minus x2. Because if I know the squares are the same, I know the magnitudes will be the same, but I can't be sure the sign is the same. And so this is precisely what we'd expect given our earlier discussion. If you think about this quadratic, x squared plus 3, it's just got a vertex on the y-axis of 3. And so what we're essentially doing is saying, suppose there are 2 values of, or suppose there's 2 values of x, x1 and x2, where the y values are the same. So I'm saying I've got a value over here, x1, let's say, and I've got a value over here, x2, let's say, and their y values are the same. They're equal to this purple value, whatever it is. I'm saying f of x1 and f of x2 are the same. It's this number. And what this is telling us is, well, look, there are 2 values that could possibly have been plugged into the function to get this y value. There's a value over here, well, that's minus some distance, and there's one on the other side that's the corresponding positive of that value. Notice that they're equally spaced around the vertex. There's 2 of these values, and they're equally spaced around the vertex, which is located at 0, 3. And so this is not a one-to-one function. This is not a one-to-one function because when we tried to force the y values to be the same, we found that the x values were not automatically the same. There's actually two different x values that are possible here. Let me make a nicer x there. That's not much nicer. Because we didn't automatically find that x1 and x2 were the same, we're not guaranteed that, we know that this is not a one-to-one function. However, something we could do is restrict the domain to make this a one-to-one function. So instead of talking about this function on its natural domain, and hopefully it's pretty clear that the natural domain here is all real numbers, instead of using that natural domain, I could say, let's just use half of that. Let's just use the domain from 0 to infinity, let's say. If we define this thing on the domain 0 to infinity, so just the piece of the line you can now see, then that purple line with a fixed y value, it only crosses the function once. And so if f of x1 and f of x2 produce the same y value, then those two things must have just been the same name because it's only for the same point. So in that case, we'd be saying x1 and x2 were the same point. For the graph you can see now, it is one-to-one. And we call this idea restricting the domain. We've gone from the natural domain of the function, which was all real numbers, to some subset of that, which takes it from being not a one-to-one function on the full domain to being a one-to-one function on that restricted domain. So we'll talk more about this in class. Thanks for watching today, and have a go at the pre-class problems, and I'll see you soon.